This lecture is on the Lagrange form of the remainder for a Taylor polynomial approximation. The idea is that you have an exact value you get from a function, you have a approximate value from a Taylor polynomial, but it is an approximation, so there will be some remainder. Now, we don't know exactly what the remainder, what that error equals. If we did, well, we would just simply add it onto our approximation and get an exact value. A remainder or an error, rather, they're given in terms of a bound within which you know you must be off by, but no more than that. So you never know exactly how far you're off by, but you know you're within some amount. And this remainder, the Lagrange form of the remainder, is given by this term. So if we're using an nth degree Taylor polynomial approximation, then the remainder will be less than or equal to the n plus first derivative at z, which I'll get back to, over n plus 1 factorial times x minus c to the n plus first. So basically it's the very next term, but we have a z here. Now z is supposed to be some value between x and c, so c where you're centering and x where you're doing the approximation, such that we maximize the value of this n plus first derivative. We want to always overestimate rather than underestimate our potential error in our approximation. So we want to pick a value of z to make this as big as possible. So first example would be over here. Arc sine of 0.4, we could approximate with these first two terms of a Taylor polynomial. It's third degree. The Lagrange remainder formula is over here. We would need to have then the fourth derivative of arc sine. See, plugging into our formula here, n being 3, we have fourth derivative at z over 4 factorial, 0.4 minus 0 to the fourth, because we're centered at 0, 0.4 is our approximation. So we need that fourth derivative, which is really challenging to get, so here it is. It's this complicated expression here. So we need to pick a value for x between 0 and 0.4 to make this as big as possible. Usually it's going to be one side or the other when this is the way you go about it. If we were to pick 0, the numerator is 0, denominator is larger, so that's not the right way to go. We want to make instead z equal to 0.4 to make the denominator smaller, numerator bigger. So plugging in 0.4 into this expression, evaluating it, times 0.4 to the fourth over 4 factorial, we would get this as our approximation. Now, oftentimes, though, you're not actually picking a specific value of z to make this as big or as small as possible. I'll show you a couple examples of what I mean by that. So here we have the third degree Maclaurin polynomial for sine x. It's x minus x cubed over 3 factorial. And we want to approximate sine of 0.1 using p sub 3 of 0.1 and find the accuracy of the approximation. So find the Lagrange remainder in essence. And so our sine is going to equal these first two terms plus our remainder. Here's our remainder term after 3 terms, so these are all 4s. And when we first plug in 0.1 to these first two terms, we just get this as an approximation. Now as far as finding our error then, the fourth derivative of sine is sine, so this f4z becomes sine z, so sine z over 4 factorial to the 0.4 to the fourth times 0.4 to the fourth. But the idea here is that we want to pick a value for z between 0 and 0.1 to make this as big as possible. So you would think, well, let's just choose 0.1 because sine of 0.1 is bigger than sine of 0. However, what you're doing then is you are using for your remainder sine 0.1 as part of it. Well, if you're trying to actually approximate sine of 0.1, it doesn't make any sense logically to have that same expression sine of 0.1 within your remainder. So again, overestimating, we just choose sine of z to be equal to 1. So that's why this expression becomes just 0.1 to the fourth over 4 factorial, because we know that sine will never be bigger than 1. And so this is our Lagrange error remainder, even though we're clearly going to be somewhat less than that. We do overestimate. So back over here to a couple more examples. Let's say we have, we're approximating cosine of 0.3, and we've used 4 terms, we're centered at 0, so therefore x is 0.3, because this is 0.3 minus 0, you can think of it as. Here's our Lagrange form of the remainder, and it's going to be either sine or cosine. I can put either one. We can figure out which one it is, or positive or negative, but it doesn't really matter in this case. And then we have 0.3 to the 5th power over 5 factorial. Once again, we don't want to use a sine or a cosine of 0.3. We want to over-approximate, so we're going to call this entire thing equal to 1. So we have 1 times 0.3 to the 5th over 5 factorial, and then that simplifies to here. Now, one thing to note is that this is only one form of the remainder. We've looked at another type, which is the alternating series form of the remainder, and cosine is an alternating series, and so after 4 terms, after the fourth degree term, you use the sixth degree term as the very next term. So actually the alternating series form of the remainder is a better approximation tool than using the Lagrange formula. This expression is significantly less than this one. In this case, here's once again our formula for Lagrange. We want to approximate e to the first power. How good is our approximation if we use a fifth degree polynomial centered at 0 and approximating at 1? So we plug everything into our formula. So we have n plus first derivative z to the x, so e to the z, 1 minus 0 to the sixth, and then 5 plus 1 factorial down here. Now, we want to make this as large as possible again, so we choose a number between 0 and 1 to maximize this. That's going to be 1. But now we run into the same issue we had a moment ago with sine and cosine, and that is that if we're trying to approximate e to the first, we don't want to actually have that same expression within our approximation for our remainder, within our remainder expression. So what we do instead is, knowing that e is somewhat close to 3 but below, I just call e to the first equal to 3 to the first, and then I find out what it is equal to there at that point. So that's my remainder if I use my Taylor polynomial fifth degree to approximate e to the first. Now, another way to look at this is, rather than saying I have a certain number of terms, how far off might I be? Another way to look at it is to say, if I want to be within a certain value, how many terms do I need to use? And so down here we have Taylor polynomial for ln x, and we want to find an error of less than 0.001. So how many terms do we need to ensure that that's going to happen if we center it at 1? And so this is a formula for the derivatives of ln x, so we can go ahead and use that formula they're giving us. Our remainder then at 1.2 is going to be the n plus first derivative at z over n plus 1 factorial, and then we want to maximize this, well, we're maximizing over here. We want to put in 1.2 because that's where we're approximating. So 1.2 minus 1 to the n plus 1. I can cancel out a few things. I plug in the derivative expression. A few things will cancel, my factorials in particular, and I get down to here. We want to make this as large as possible, so therefore I'm going to make z small because it's in the denominator, so I make z equal to 1. So in effect, this z to the n plus 1 then drops out, and I get down to 0.2 to the n plus 1 over n plus 1, and I want that to be less than 0.001. So this is now my simplified remainder in terms of how many terms I'm using, and I want to find out a value of n to make this within my desired error value of 0.001. You can do a little bit of algebra with it by flipping things over, changing inequalities, and eventually you've got to use trial and error to figure out that the least number of terms that would be required to get an approximation within 0.001 would be 3 terms. Another way to look at it, you can see graphically, is here's the function ln x, and what I'm going to do is increase this, and what will happen is as I go up higher, this gray band will go around my center. So I'm centering it here at 1, and I want to see how many terms I need in order for these functions, in this case the green and the black, to differ by less than 0.001. And if they differ by less than 0.001, the gray band appears. And at this point, using only first degree, my approximation point t is not within that band. So if I use another term, you see now I've got this parabolic approximation. If we again would do the black minus the blue to get the gray band, because it's got to be less than 0.001 for the band to occur, I'm still not quite there. Then if I go up one more term, then clearly I'm within that band. So here's my polynomial for it, and that's enough terms so that my approximation falls within that error value. And one more example of this idea is actually up here. So sine of 0.3, and then I want to be within 0.001, and so n plus first derivative of z, which again I'll just make 1 because it's a sine or a cosine. 0.3 minus 0 to the n plus 1, and then n plus 1 factorial. I want it to be less than this error value, and then once again I use trial and error, starting really at 0 and going up as far as I need to go in order for this inequality to be true.